Welcome to the Unit 0 Section 3 video on properties of exponents. Alright, we want to talk about how exponents work because as we move on to the next section we're going to be working with polynomials, and as we multiply polynomials together and we add and subtract them, we need to know how to work with any variable that has a power on it. So let's start off by talking about the first rule to work with exponents, and that is the product rule. So recall that an expression of the form x to the n is a power. The base is x and the exponent is n. So I have listed here powers with a base 2 from 1 to 10, and we are going to use these values in this exercise to just see how exponents work, okay? So in this first example, we have 4 times 16. Well, 4 can be rewritten as 2 squared. 16 can be written as 2 to the 4th, and 64 can be rewritten as 2 to the 6th. Okay, let's move on to the next one. 8 can be rewritten as 2 to the 3rd. 16 can be rewritten as 2 to the 4th, and 128 can be rewritten as 2 to the 7th. And then this last example, 8 is still 2 to the 3rd. 32 can be written as 2 to the 5th. And 256 can be written as 2 to the 8th. Okay? So now that we have all of these rewritten as a base 2 power, let's look at the exponents and see if we see a pattern emerging. So we've got 2 and 4 in this first one, and then on the other side of the equal sign we have 6. In the second one we have 3 and 4. And we're going to do something with those to make it equal 7. And then we have 3 and 5, and we're going to try to make something equal 8. Well, what operation can we use to make all three of those statements true? Well, 2 plus 4 equals 6, 3 plus 4 equals 7, and 3 plus 5 equals 8. So the takeaway that we can have with this is that if we add the exponents, then we can get the answer. In other words, if we add the exponents of two things that are being multiplied with the same base, then the result is that base to those exponents that are added together. Okay? And that is the product rule. So this is the product rule laid out for you. And it simply states that for any number a and all integers m and n, a to the m times a to the n equals a to the m plus n. Okay, if you've got the same base and you're multiplying them together, you can just add the exponents. So let's do a couple of examples with this. Let's go to the world of geometry for a moment. Let's find the measure of the area of this rectangle that's on the right. Well, how do we find the area of a rectangle? Well, area equals length times width. Okay, so the length of this rectangle is x to the 4th, and our width is x to the 3rd. Well, if we multiply those together, we can add the exponents since it's the same base. It's base x. So if we add together our 4 and our 3, then we end up with x to the 7th as our answer. And since our length and width were given in terms of x, it's perfectly acceptable that our area would also be in terms of x. Okay, let's move on to example 2. Let's simplify this expression. Well, if we want to simplify this expression, let's start off with just the numbers that are in front. We'll just take care of the numbers that are in front. We're going to group them. This is called grouping like terms, okay? So we're going to do negative 5 times 3 times 2/5. Then we're going to group our next set of terms together. So we have x squared, we have x to the 3rd, and we have just x. Okay, all our x terms get grouped together. Finally, we're going to group together our y terms. So we have y squared, and we have y to the 4th. Well, let's multiply each of these groups. So if we multiply negative 5 times 3 times 2/5, what we end up with is negative 6. If we multiply x squared, x to the third, and x, well, they're all the same base, so we're going to add the exponents. And then for the y's, also the same base, so again, we are going to add the exponents. Now, after we do all of that, we're going to end up with negative 6, x to the 2 plus 3 plus 1, that gives us x to the 6th, and y to the 2 plus 4 gives us y to the 6th. So our final answer is negative 6 times x to the 6th times y to the 6th. Okay, now let's move on to our next rule, which is power of a power. Okay, when we're dealing with power of a power, well, let's see what kind of result we can get using the rule we just learned. Okay, so we can rewrite 5 squared to the 4th as 5 squared times 5 squared times 5 squared times 5 squared. Well, we just learned a rule as to what we do when we multiply things that have the same base. We can add the exponents. So this can be written as 5 to the 2 plus 2 plus 2 plus 2. And when we add all that up, we end up getting 5 to the 8th. Let's move on to the other example. X to the 6th squared. Well, that's just x to the 6th times x to the 6th. If we multiply two things with the same base, we're adding the exponents, and we get x to the 12th. Well, math is all about patterns, so let's see if we can see any patterns. Our exponentials are 2 and 4 in the first one, and we end up getting 8 as our resulting exponential. On the other example, 6 and 2 are our exponentials, and we end up with an exponential of 12. Well, what can we do to make both of these statements true? We can simply multiply the numbers on the left to get the one on the right. So 2 times 4 equals 8, 6 times 2 equals 12. So you can find the power of a power by multiplying the exponents. And that leads us right into the power of a power rule. For any number a and all integers m and n, a to the m to the n equals a to the mn. So let's do an example of this. We have x to the 6th to the 8th. Well, to find the result, all we have to do is x to the 6 times 8, and that gives us x to the 48th. And that's it. That's our example. All right, now let's talk about power of a product, okay? This is the last rule that we're going to be looking at involving multiplication. Okay, so let's consider these problems. We've got xy all to the third. Well, we can rewrite that as xy times xy times xy. Well, everything's just being multiplied together, so we can rearrange these terms in any order that we'd like. So let's do the x's together. We have x times x times x, and then we have y times y times y. Well, we can rewrite the x terms as just x to the third, and we can rewrite the y terms as y to the third. Let's do the same with this next example. We've got 4ab to the 4th. So let's rewrite this as 4ab times 4ab times 4ab, and one more times 4ab. Well, let's do the same thing. Let's group our 4's together. So we have 4 times 4 times 4 times 4. Let's group our a's together. So we have a times a times a times a. And then we've got our b's that can be grouped together. B times b times b times b. Well, each of those groups can be rewritten as a power of 4. So we have 4 to the 4th, we have a to the 4th, and we have b to the 4th. And I think you're very quickly seeing the pattern here. If we take something that's multiplied together and raise all of it to the 3rd, then we can raise each individual term to the 3rd. Same thing goes with the 4th power that we have in the second example. If we multiply these 3 items together and take it all to the 4th, well, we can take each to the 4th and then multiply them together. So that's our power of a product rule. For all real numbers a and b and any integer m, ab all to the m equals a to the m times b to the m. So let's work with this rule that we just found and do an example. All right, let's go back to some geometry. Let's find the measure of the volume of this cube that is here on the right. Well, the volume of a cube, you may think length times width times height. And if you were to think that, then yes, you would be correct. But we can actually write the volume of a cube a little bit more succinctly. And that's because every single side, width, and height, the length, width, and height of a cube are all equal. So since they're all equal, then we could just do side times side times side, which would be side cubed. Okay? So, since we know the length of one of the sides, let's plug that in for our side. We've got x squared, y to the 4th, and all of that's going to be cubed. In fact, this is where the term cube comes from. When we have something to the 3rd power, we say it's cubed. This example shows you why we call a 3rd power cubed. All right, back to the problem. If we use our power of a product rule, then we can take each of these individual terms on the inside that are being multiplied together, and we can take each of them individually to the 3rd. So we've got x squared to the 3rd, y to the 4th to the 3rd. Well, now we have another rule we can use. Since we have a power to a power, we can multiply those powers together. And finally, doing that, we get x to the 6th, y to the 12th. And that would be the volume of our cube. Okay, now let's move on to the quotient rule. Okay, so now we're going to talk about division a little bit. Let's do a similar exercise to how we did toward the beginning of this video with multiplication. This time we're just going to do it with division. So we have 81 over 27 equals 3. Well, we can rewrite all of these in terms of something that's base 3. 81 is 3 to the 4th. 27 is 3 to the 3rd. And we can write 3 as 3 to the 1. 27 is 3 to the 3rd. 3 is 3 to the 1. And then 9 is 3 squared. And then finally we have 243, which can be written as 3 to the 5th. 9, which is written as 3 squared. And then 27, which is 3 to the 3rd. Well, let's see if we can find a pattern in these, okay? So on the first one we have 4 and 3, and we're going to end up with a result of 1. On the second one we have 3 and 1, which is going to give us a result of 2. And then on the last one we have 5 and 2, which are going to give us a result of 3. Well, what operation can we do to make all of these true statements? Well, 4 minus 3 is 1, 3 minus 1 is 2, and 5 minus 2 is 3. So what we find is we can divide powers that have the same base by subtracting the exponents. And that gives us our quotient rule. For all integers m and n, and any non-zero number a, and a needs to be non-zero because we cannot divide by a to the m divided by a to the n equals a to the m minus n. So let's do a couple of examples using this rule. Let's simplify b to the fifth over b squared. Well, b to the fifth over b squared is simply b to the 5 minus 2, and so that gives us b cubed, and that's our answer. Let's take it up a notch. Let's go to example 6 here. Simplify a to the fourth, b to the third over ab squared. Well, what we want to do first is we want to gather our like terms. So we're going to have a to the fourth divided by a, and then we're going to have b to the third divided by b squared. And then when we do that, we can separate our terms. So we end up with a to the 4 minus 1, because we're simply subtracting the exponents, and b to the 3 minus 2. And when we evaluate that, we get a to the third times b. And we don't have to write the first power, because if we don't have a power on it, then it's understood to be the first power. So that's our first rule for division. Let's move on to another rule for division, and this is power of a quotient. Okay, so let's consider this problem. We have x over y all to the third. Well, let's rewrite this, because we know if it's to the third power, we're going to multiply it on itself 3 times. Okay, well, on the top, if we multiply all of this together, we end up with x times x times x in the numerator, and we end up with y times y times y in the denominator. And x times x times x can be rewritten as x to the third, and y times y times y can be rewritten as y to the third. So very similar to how we had with multiplication, you probably notice a pattern here. And that pattern is if everything that we are dividing is all taken to a power, then we can take the individual parts to that power. And this is called power of a quotient. For all real numbers a, non-zero real numbers b, and any integer m, a over b all to the m is equal to a to the m over b to the m. So let's do an example using this rule. We're going to simplify x to the third over x squared all to the fifth. Okay, so the first thing we're going to do is we are going to separate out our top and bottom. So we've got x to the third to the fifth over x squared to the fifth. That's our power of a quotient rule being used. Well, then we can rewrite this as x to the 3 times 5, because we have power of a power, and x to the 2 times 5, because again it's power of a power. So x to the 3 times 5, that would be x to the 15th. X to the 2 times 5 would be x to the 10th. And we finally use our quotient rule. X to the 15th over x to the 10th is the same as x to the 15 minus 10. And so our final answer is x to the 5th. Now, in math, we often have options. So let's look at this problem one other time and see what other options we could have used to solve this problem. Because you'll often find that when there's more than one way to do things, usually one way is longer than the other. So let's see if we can figure out a shorter way to do this problem. Well, we can start with what's on the inside. And if we start with what's on the inside, we have x to the third over x squared. We can go ahead and subtract using the quotient rule. Subtract our exponent. And then we keep our fifth on the outside. Well, what's x to the 3 minus 2? Well, that's just x. And so we end up with x to the fifth. So we got to the same place, but it was a much shorter route. So it's really up to you and what you're comfortable with as to which direction you take. Some ways are going to be obviously shorter than others, but it's really up to you to decide. Neither way is a wrong way to do it. One's just longer than the other. If you were to do it the first way we did it, that's perfectly acceptable, and it's perfectly fine, and it gets you to the right answer. And that's really what we're looking for, too. But if you happen to notice this other method of doing it, that is also correct, and it's all up to you how you want to attack the problem. Okay, let us move on to two more rules that are kind of on their own. Okay, and the first of which is the zero exponent rule. There are two ways that we can simplify a to the third over a to the third. Now, you may very obviously already be thinking, well, that's just one, right? Well, you're correct. That would be the first way that we can look at it. A to the third over a to the third. We can write that as a times a times a over a times a times a. And really all that is 1, right? But we have also just learned some rules that we can use. So let's look at it using those. A to the third over a to the third. Well, that's the quotient rule, so we can use that to do a to the 3 minus 3. And a to the 3 minus 3 gives us a to the 0. Well, we have just found two ways of writing a to the third over a to the third. And since they both equal a to the third over a to the third, that being 1 and a to the 0, we can set those equal to each other. That's the transitive property. So since a to the 0 equals 1, we can in general say any non-zero number raised to the 0 power is equal to 1. And that's our zero exponent rule. For any non-zero number a to the 0 equals 1. So essentially we're saying, as long as a is not 0, then we can take anything else, and if it's to the 0 power, then it's just equal to 1. So, are you ready for the easiest example that you're ever going to see? Let's simplify all of this mess to the 0 power. Well, it's 1. Because it's all to the 0 power. So, since it's all to the 0 power, then it's equal to 1. That's it. It's that simple. All right, the other rule I want to look at, this is the final one for this section, is the negative exponent rule. So we're going to look at this very similarly to how we did the zero exponent rule. Let's look at two ways to simplify k squared over k to the 7th. So we have k squared over k to the 7th. Well, we can write k squared as k times k. And we can write k to the 7th as k times k times k times k times k times k, and one more, times k. Well, two k's on the top are going to cancel with two k's on the bottom. So we're going to be left with 1 on the top, and then k times k times k times k times k on the bottom. Well, we've got 5 of those now on the bottom after we do that cancellation. So we can rewrite the bottom as 1 to the k to the 5th. 1 over k to the 5th. All right, let's look at another way. And let's look at it using the rules that we've established up to this point. We've got k squared over k to the 7th. We can write that as k to the 2 minus 7 because of the quotient rule. And that gives us k to the negative 5. And again, we've ended up with two things that are equal to k squared over k to the 7th. So therefore, those two things, being 1 over k to the 5th and k to the negative 5th, must be equal to each other. And that suggests the definition for negative exponent. For any non-zero number a and any integer n, a to the negative n is equal to 1 over a to the n. So let's wrap this up by doing one final example. Let's simplify this term. Well, let's start by grouping things together. These types of problems lend themselves to organization. As long as you can stay organized, then you should be successful with these problems. So let's start with things that are just numbers. We've got negative 6 over 18. Okay? Now let's group our r's together. Well, we've got r to the 3rd on the top, and we've got an r to the negative 7th on the bottom. Let's group our s's together. We've got s to the 5th on the top, and we've got an s to the 5th on the bottom. And then finally, we don't have any t's on the top, so we'll put 1, but we do have a t to the negative 2 on the bottom. All right, well, the first term can be reduced, right? It's just a fraction, but it can be reduced. So we end up with negative 1/3. Now let's use the quotient rule for our r terms. So we're going to end up with r to the 3 minus 7. Actually, 3 minus negative 7. It's very important that you are careful with your signs, that you don't lose anything along the way. Then we have s to the 5 minus 5. And then t to the negative 2 in the denominator, using our negative, or I should say our negative exponent rule, we can pull this to the top, okay? So it just becomes t squared. Okay, well, we are on our way. We're almost there. Let's clean this up a little bit. We've got negative 1/3. R to the 3rd minus a negative 7. Well, that's going to give us r to the 10th because it's the same as 3 plus 7. S to the 5 minus 5 is going to give us s to the 0, and we still have t squared. Well, s to the 0 we know is 1, so we can drop that term. And so now everything else is going to stay. So I'm just going to rewrite this all as one fraction. So negative r to the 10th t squared over 3. And that would be our answer. Now that we have some exponent rules under our belt, we can move on to the next section, which will be on working with polynomials.